Hi, and welcome to today's webinar with Civan lasers. This webinar will look at how to master dynamic beam laser technology, an emerging solution in the field of welding that can offer unparalleled capabilities and shaping and adjusting the laser beam on the fly. It will also provide insights into dynamic beam laser welding to help you understand the latest advancements in laser welding techniques, provide insights into the unique capabilities of dynamic beam lasers, and offer practical tips for enhancing welding efficiency and quality. It will also demonstrate how Civan lasers can help you to leverage this technology to achieve the best results. My name's Keely Portway, and I'll be your moderator today. And I'm very delighted to introduce our expert speaker, Dr. Robert Bernard, Application Lab and Branch Manager at Civan Lasers. In terms of the format of today's webcast, Robert will do his presentation, followed by a short Q&A section. You can ask the questions as you think of them using the box at the bottom of the screen. You don't need to wait until the end. So, without further ado, let's get started. Robert, the floor is yours.
Thank you very much. I'm very happy to present today the dynamic beam shaping and as well as getting the precision of welding right. So let's start with a short overview about Civan Lasers. As you know, I'm here from Germany, but Civan Lasers itself is an Israeli-based company where we have 200 employees located in Jerusalem. But we are the manufacturer of this very interesting laser source. And today I really want to give you insights into the precision welding using our technology, using the CBC coherent beam combination, as well as inspire you to push the boundaries of laser material processing, which means we're gonna perfect and get the really insight into the technology. And let's start with our laser and what the dynamic beam laser can do. And on the bottom right, you can see beam shaping. We are looking into the focus of our laser, and we are able to do dynamic beam shaping. And this is so to change the energy intensity during laser welding. So we offer a laser with 7, 14, and 28 kilowatt laser power. And what we are doing is coherent beam combination. And with this, as you can see, just a few shapes here, we can do arbitrary beam shapes. So how does it work is the question. And we are actually the provider of the strongest coherent beam combining laser for laser material processing. And first, I would like to start with the basics and get you into the technology. So we are working with coherent beam combination. What does that mean? We have multiple laser beams that come from an amplifier stage that are combined. And from grade 11 physics, you might know the interference patterns that can occur with using lasers. And this is exactly the concept we are using. We have multiple laser fibers, 32 all in all, and they are doing constructive and destructive interference. How can we control that now, you might ask? We are using the phase modulators you can see on the left that allow the shifting and the control of the resulting interference pattern on the right. And the great thing about this, it's completely electro-optically, which means there are no deflectors, there are no mirrors. It's all based by doing it with the phase modulators. And these phase modulators are really, really fast. Really, really fast means 50 megahertz of speed. And at this 50 megahertz, we can create these interference patterns. So to speak, we have a way of generating very dynamic beam shapes. And you can see in the top right, there is the individual interference patterns. But looking at this way doesn't really make sense, but we are really, really fast. This is just an illustration, which means the energy we have as an average power density then in turn means we are able to do whatever we want. And here it's a smiley face. So the beam shape is generated with interference using coherent beam combination. And this actually means that we are able to do inside the focus, we are able to do arbitrary beam shapes. So this, compared to other lasers, opens completely new degrees of freedom. You can see interesting beam shapes here on the right that are all generated using our laser inside the focus. So what we can do is the beam shaping, of course, but we can also change the beam shape frequency, which is the frequency at what the shapes are generated. We can also always like kind of make movies with our beam shapes, and these motion pictures are like shapes of sequences, as well as doing focus steering, but more on that later. Let's start by going through these new degrees of freedom for laser welding. So what you do is you design your own beam shape, and by designing your beam shape, we are actually able to do tailored to the material, tailored to your needs, the beam shape geometry, which means with the shape geometry, we can also change the energy distribution in our focus spot, as well as changing the beam motion and the overall focus. So this means whatever your material might require and what your challenge might need, we are able to do different beam shapes. This can be anything you can imagine, so the sky is the limit. Here are just a few of them, even some with some motion. And what I really want to point out here, this is not done by doing any moving mirrors. It's really electro-optically. On the right side, you can see caustic schematically, and this all happens inside the envelope, inside our focal plane. So we're talking about around 600 micrometers of size inside this focus spot, and we are able to do fine details down to just 50 or 60 micrometers. So, but why is the question? And in order to master this, and we can now do beam shapes, and even though the energy distribution on the top one looks familiar to other lasers, but actually by changing the frequency, we can also get the steering effect. And by now using different beam shapes and by working with these beam shapes adjusted to the material, we have the opportunity to here change the lifetime of a melt pool. So we're looking into a weld from the top side. You can see the laser weld, the laser passing on the material, and they have the same power, the same energy. But what you can see is that the bottom melt pool closes faster than the top one, which in turn means that we have a different energy distribution, that we have a control of the solidification rate, so to speak. So this is just an example how that can work. And now I want to go into the theoretical details, what that does. And actually, by just changing the beam shape and changing the direction, we are influencing the velocity, and we are also influencing the flow of the melt pool. And this is really, really interesting because for this material here, aluminium series, we are actually experiencing a lot of cracks if you're using the shape, the triangle shaped in a kind of backwards direction. But if we want to work with the melt flow and increase its size, by using the same power, of course, we're able to elongate the melt pool, and this then means we are able to get rid of a lot of cracks. So this is just one example. We go into more detail later, but beam shaping really has a very big influence on how the solidification works. Actually, also what we can do, because our beam shapes are generated completely electro-optically, we don't need to spin our optics. So if we are welding some kind of weld seam and we have to do some seam tracking with our beam shape, the robot or the machine doesn't have to rotate the workpiece or the optical head. We can all do this internally. So this can be seen also on this video, where you see the wave front and the front of the two dots that are actually aligned to the weld seam. And yeah, this is a great way to compensate for gaps and also work on really fast welds with difficult contours. So far, on the shape in general, but there's more to it. As I told you, we can go up to 50 megahertz shape frequency, which in turn means how fast these beam shapes are generated. On the left side, it's an illustration how you can think about that, but actually it's more to how fast these beam shape is generated, and this also works on how the melt pool and how the keyhole, as well as the fluid dynamics and surface tension react to it. So what we see and what our results backed by simulations show, that the keyhole here on the right side is really depending on what frequency we are working on. So at only 2.6 kilohertz, there's a lot of spatter and it's very violent, compared to something that works very fast, and the higher frequency can yield into lead to a very big open keyhole that doesn't have keyhole collapses in regard of losing and getting spatter out of that. So here's an interesting beam shape that has kind of a ring with the centralized dot. Usually you do something like this for getting the maximum penetration and at the same time working and getting into the material, but also
Hi everyone, sorry about this. We've lost Dr. Robert for a minute. We're having some technical difficulties. We're just trying to get him back. Apologies.
I hope I'm back now.
You are.
Oh.
Thank you, Robert. Sorry.
Let me share my screen again and let's continue, I guess. Okay, so where were we? We were talking about shape frequency. And this shape frequency actually is not only on simulation, but also when doing aluminum welds. One Personal favorite of mine is the welding of aluminum die cast. We're also going to talk about this more in detail, but to illustrate the influence on porosity, you can see that differences in the shape frequency, how the laser shape is generated, actually results in less or more less porosity. This here is a bead on plate with 2.8 kilowatts and 150 millimeters per second. So you can see that we are able to reduce porosity when welding these materials with a high amount of porosity. But that's again not all. We're talking about more influences we have, and still with the shape frequency, it's also about intermetallic mixing. So intermetallic mixing here means we are doing different shape frequencies in order to get the intermetallic mixing of the top material in overlap configurations just right with the bottom material. So in this case, we have aluminum to copper welding, 7 kilowatts, 200 millimeters per second in the overlap configuration. And here we are using a beam shape that's kind of a spiral. And this spiral now changes how fast the spiral is generated electro-optically. And what we can see in the results is that the shape frequency has a very big impact on how the mixing works. So all the process parameters are identical, but the welding results in different dilutions. So when you go from left to right, we can see 100 kilohertz. It's just a few copper-based material goes up into the weld, but we can very well increase that on the right side by doing more and more dilution due to the shape frequency. There's more again, I guess. The shape sequencing. We were talking about single beam shapes and how they are made up. And now we are actually able to do more than just that. And this is fascinating because if you know a beam shape that does the intermetallic mixing, and if you know a beam shape that works well for deep penetration, I think you can start and combine the positive effects of the two. So here you can see how in our software it's set up. We have multiple different beam shapes, and then you can define the frequency we just learned about. And now we have the duration, how long a beam shape is present and how long the material sees the beam shape. And to see this in action, again, some nice high-speed footage on some stainless steel. Here you can actually see the flipping and the change of the beam shape at different frequencies, which means different the times, how long they are visible and for how long they do something. And this is here just to illustrate that we're actually able to get the beam and the melt pool motion just right to get a very smooth and calm process and actually reduce pores and spatter. So as you can see, one beam shape on the left side really leads to a lot of spatter and material flying outside of the beam. But if we increase in speed, the melt pool really becomes calmer and in turn results in better welding results. This actually is also really interesting, and something we observed is by lasing with just a single beam shape, we get a lot of cracks, especially in thicker material. And doing the different shape and another shape, it's also a problem that the cracks are still there. And the only solution is to do the alternation between two different beam shapes, and then all of a sudden it becomes good, so that we have no cracks, no inclusions. And so there's a way of keeping the keyhole open, as well as making sure that weld penetration is just right. This is also true for some hairpin welds we did. Here it is set up in a way that we have a beam shape set up directly over the hairpins, and by doing some time in this beam shape and then going over to a more random beam shape, we are also able to get the connection and the porosity out of the material without damaging the insulation and reducing pores specifically. So now to the final thing I get about our laser. The beam works in 2D. We are also able to do 3D beam shaping. And we have a single mode laser, which already means that we have a very long focal distance, but also we are able to do the focus shifting using our electro-optical beam, coherent beam combining. And the focus steering in these frequencies really helps to get the best and the best results in deep penetration welding, but also working on lower depth, so we can adjust A for the workpiece and B for the things the material itself needs. So by doing this focus steering, in some installations, we can also get rid of the a Z-axis, a dedicated Z-axis. In regard of, here you can see that for welding hairpins, it increases the size of the working field, as well as working and shifting the beams so that all the welds are in focus, and we can adjust for inconsistency that might be to a jig or something. So yeah, we are able to do the focus autocorrect here. And now we talked a lot of about the dynamic beam laser. This is just the conclusion before we go to the case studies and the welding examples I want to showcase. First, we now know that the dynamic beam laser is able to do dynamic beam shaping. We are able to control the shape frequency, as well as doing shape sequences. We have a high beam quality, as well as focus steering, that finally can lead to focus autocorrect applications and makes it really broad for a wide use of laser material processing. And that's the keyword, and my welding results and case studies will be on the next. We already touched the surface of what's possible, but this is just some applications where this laser is really capable of pushing the boundaries and getting into the material and beneficial process parameters, and it can be developed. So the challenges automotive EV are zinc coated steels. This is something our dynamic beam shape sequences can get rid of. The powertrain with electromotors is also something that we can actually really improve the porosity. Other aluminium parts in the wheels, deep penetration wheel welding is the thing with adjusted and very no porosity welds. As well as aluminium die-cast parts found in automotive water cooling solutions and so on, which is usually a challenge, and we're going to talk about that more in a second, as well as battery coolers with a wide interface that is needed for leak-tight welding, as well as copper busbar welding. So EV's battery cooling plates. Here we have a small case study. Usually these materials are welded in vacuum brazing furnaces, which means that's a slow, very energy intensive process and needs a lot of space for this kind of machine. And with our dynamic beam laser in comparison, we can save a lot of cost per part because we are way faster, as well as we have a lower power consumption. That in turn means we are saving on the running costs. And of course, we are more energy efficient with a nice welding machine with enough space. We can also work very efficient on welding these parts and reduce the carbon footprint. So the welding results in this regard aluminium, as well as welding 3000 series to 6000 series, as well as 6000 to 7000 series. And what you can see here, and I want to give an example on the left aluminium in a moment, that our laser is welding these like with very nice cross sections, but also very fast. So here we are talking about the welding of aluminium 5754, and we are reaching up to 500 millimeters per second. And while being this fast, we have these coupons that are leak-free at 2 bars. And then it's all about your application and your problem, where we can improve and go on to more details with this. But generally, how is it done? We are using beam shapes and beam frequencies that make the interface very wide. We have enough power with our systems in order to get the welds done that fast and get the weld dimensions just right so that the material is leak-free welded. This also is true for 6000 aluminium. Here we usually have problems with porosity because the keyhole collapses quite frequently. Even at lower speeds, you can see that on the left side, that there's sometimes the keyhole collapses and then we have a pore inside the material. And this is even though we are using and comparing to a static ring laser. With our dynamic beam laser, we're actually able to do the welding and making sure that by a specific beam shape, here it looks like a boomerang kind of, that keeps the keyhole open and distributes the energy just right in order to get the melt pool and the material to flow like beneficially for our process. So despite the scratches on the part, it's very nice weld in terms of the penetration uniformity as well as porosity. So this actually means we can weld up to 100 millimeters per second this 6000 series aluminium, and usually there are cracks occurring as well as porosity. But if we use our boomerang shape or V-beam shape, we can reduce the porosity, and because it also adjusts the flow and the melt pool solidification rate, we are reducing our solidification and the solidification cracks. But this is not all. Again, we are very broad on what we can do, and something I also personally enjoy is welding thick materials. It's always fun to see these very thick metals that can be welded by just the power of light. and just the power of light here with an asterisk with dynamic beam shaping, which means conventional hybrid lasing processes need multiple passes, but because our laser can do more than just passing like welding, we can also assign additional functions like melting the filler material, remelting at the end of the weld. So we are actually able to reduce the number of passes. While also, because it's a laser process, we don't need to have an arc burning. We are actually able to be way faster than conventional processes. So, and here you can see again the influence of beam shaping and as well as changing between different beam shapes. And what this leads to actually is, come on, I can do this. What this actually do is welding really thick sections. So we're talking about mild steel, 70 millimeters, and this welding this with a conventional laser without vacuum, of course, is a challenge. But by doing also the focus steering, we can go very, very deep into the material. On the other side, also for thinner materials with a small gap, you can see that we are able to do the weld. Here, we didn't use any filler wire. We would be able to fill the material using filler wire here. So filler wire is also a thing because of course, if we have to bridge a gap, we need some material to get there somehow. And we are currently working on welding with filler material. And this is also then a process that we are capable of doing. And here again, doing the beam shaping and getting the beam shape so to a very reproducible melt the filler wire. It's very nice to get a process that then results into a very even and porosity-free process. Speaking of porosity, I want to also deep dive into the aluminium die casts. Aluminium die cast from the process itself, it's made by die casting and high pressure die casting with a lot of diluted gas. And if we heat the material up and bring it to the melting point, all the material or the gases are boiling kind of and leaving the material. So with conventional lasers, you observe a lot of porosity, blowholes, keyhole collapses. And that's why the process is not really established in aluminium die cast welding. What the companies do usually is doing friction stir welding, which is a very slow and process that is very specialized. And yeah, this process is not the right process for really productive environments. And also with laser welding, it has many advantages. One of them here is that we can weld the parts with the components inside because we have such low energy input and no vibrations, as well as we are able to do the rework of 40 welds with our laser. So this finally means we are able to do the welding of parts, of die cast parts with very low porosity. We can see this here again. Here I changed the frequency of the weld, of the shape frequency. And you can see that again, we have the ability of changing and removing porosity while welding. And I'm really happy about these welds where we're able to, in this cross section at least, to reduce the porosity to a minimum. And finally, regarding the hairpin welding, this is also something really interesting. There are sequences of different beam shapes. We saw that before, and by combining the two, we're actually able to get superior results, high cross-section, and very, very low porosity. So this I think encourages to dive deeper into beam shapes and how they work with the material. So what we've learned so far is that the capabilities of the dynamic beam laser has the control over the thermal distribution and thermal gradients in space and time, because we can work with the beam shape itself, but also with the frequencies. And on the other side, we can do the control over the dynamic flow, which also is the result of all the parameters we just talked about. And this then leads into stabilizing the keyhole and the melt pool, as well as we are able to tailor our weld geometry if you want to have something wider with a wider interface for leak tightness, for example, or if you want to have something with a very small energy input. Our laser is very flexible in this regard. And furthermore, with the solidification, we are also able to adjust and even, and to some extent, to set the phases that are occurring inside the solidified material, because we are able to really precisely control how the weld behaves and the melt pool cools down in terms of solidification. So with this, thank you very much. If you're interested in seeing this yourself, I'm running the App Lab here in Hanover, and I'm really happy to host all of you. And thank you very much.
Thank you very much, Robert. That was brilliant. Really interesting presentation there. I really enjoyed it. And it's now time for the question and answer section. We've had a few questions come in. Don't worry if yours doesn't get answered. We will forward those on after the webcast. So I'd like to start with this one. Robert, what exactly are the differences between the dynamic beam laser compared to a conventional laser with a scanner?
So the main difference is that we are not like for the beam shaping. Usually you would have beam shaping that is done by a high frequency oscillating, which we can also use. And if you have a scanner for deflecting the beam, that can be added to this. But we are way faster, and we are actually able to do the beam shaping inside the inside our focus spot. So this is different in terms of how, because we're doing it electro-optically.
Okay, brilliant. Thank you. And what are the applications best suited for the dynamic beam laser?
So my personal opinion is that our laser is best for things that cannot be done in general terms, and we saw that on the aluminium die cast. This is something I really like to work on and emphasize that this is, I think, something where we can really push the boundaries of what's possible. But this is also true for the welding, high-speed welding of thinner materials. But at the same time, because we have a laser that has like 14 or even 28 kilowatts, this opens up the door for high power, thick metal welding. And I think there's also a lot of potential for welding these types of materials.
Fantastic, thank you. We've had a question come in. have you already considered using the same technology for drilling, engraving, or other types of laser materials processing?
So we're actually working on cutting, but me personally, I'm the welding guy now, so I welding applications, but actually there are applications I know of that our lab can also do. Like especially one thing would be 3D printing, like additive manufacturing with metals, because the control of the heat input by using different beam shapes can really also improve the quality of 3D printed materials. So that's definitely a yes.
Perfect, thank you. And somebody's asked, what is the approach to finding the right settings and what role does AI play here?
So this is a great question and something we are really working on. There are different approaches. Approach number one, and the conventional approach, I guess, is to do some trial and errors. And we saw that with some knowledge, with kind of an handbook of shapes that we know work for some kind of material and some kind of process, that is really helpful. But additionally, also working with AI in order to get results, and our laser has all the capabilities of connecting to AI. We are able to further develop this. It turns out that fluid simulations are kind of energy and time intensive. So I think the solution will be somewhere in between by having kind of an operator handbook, which beam shape is the right for the right material, but also getting AI involved in bridging the gap between tedious simulations as well as the knowledge we have. We have, and especially for porosity, it's great.
Perfect, thank you. And what types of machines can be equipped with this technology?
This actually is a question I can answer really quick. So we are the manufacturer of the laser beam source. So what we've done previously is integrating our machine into existing machines. And this is something we are working on in gantry setups, in a metal AM setup, but also in robot setups. But we are always looking also for integrators that feel ambitious and pushing the limits in order to integrate our laser into this kind of setup. So yeah, I think the machines really depend on the use case. It's also very well possible to do retrofits of you have a hybrid setup where you're welding ship metal, but to get your productivity way higher, then it would be possible to incorporate and add this laser at a later stage.
Excellent, thank you. And somebody has asked, how do you measure the behavior of your weld pool in real time? Which tools do you use?
So this now in a production and research environment. When I'm doing the process development, I'm actually working with high-speed cameras. That's the way where we can see the interactions and what you saw with the melt pool. But there's more to it. We have a coaxial camera that is a little bit slower, but that can be incorporated into your process, into the industry processes that monitors the behaviors. But we are also open for collaboration, like welding sensors that are based on spectroscopy, that are based on OCT, and all kinds of radiation that comes from the melt pool, which means this actually depends on the requirements the user then has.
Okay, brilliant. What's the minimum adjustable laser power, please?
So going back to the initial, I think I can just press 1. Because we have so many fibers and because we have multiple amplifiers, the minimum power the machine we usually have is 7 kilowatts. But actually, if you want to try out some different powers, we can of course modulate them. I would say on my 14 kilowatt machine, we can go down to about 1 kilowatt minimum. But then there's a small jump. We can still do beam shaping when not turning on all amplifiers, which means we can do, let's say the beam shaping starts at 200 watts laser power, goes to around 500. Then there's a jump to 800 watts, and then we have the full spectrum of 14 or 28 kilowatts. So this actually depends on your use case, and for additive manufacturing, it doesn't really make sense to have like 14 kilowatts laser power. So it's very scalable. And if you're open to sacrifice some beam shaping size, kind of, it's also adjustable in this regard.
Excellent, thank you very much. And does dynamic beam shaping also make sense for conduction welding or only for keyhole welding?
So I think it's very interesting in this regard because we can adjust our power and our beam shaping, and we can combine the two in one process. But I think what you're asking here, I think conduction welding also makes some sense. But yeah, like the strong point is setting the keyhole and doing this for keyhole welding with high intensities. But by tailoring the beam shape to have some conduction effects, and this is tailored to the beam shaping, doing the cooling rates just right, I think we are also capable of doing conduction welding.
Perfect. Thank you so much. Robert, thank you so much for taking the time to answer everybody's questions. We've had quite a lot come in today. But this brings us to the end of today's webcast. Just to say another big thank you to you, Robert, to the whole team at Civan Lasers for taking part in this webcast with us. This will be available on demand for the next 12 months after today on the Electro-Optics website. That's www.electrooptics.com. But please note that the live Q&A obviously won't be in action in the on-demand version. So thank you very much, everybody. And thank you, everyone, for joining us. Thank you. Bye-bye.